Let's talk about a two-sided hypothesis test for proportion. Here's the idea behind hypothesis testing. We have a hypothesis, which is a guess about what is true. We collect data to test the hypothesis, and we plug data into a formula, and then use the result to determine whether or not our hypothesis is true. For example, I have a pair of 7-sided dice in my office. Are they fair dice? Here's me rolling one of the 7-sided dice. There's a 7. Okay, so I have the pair of 7-sided dice in my office. Are they fair dice? In other words, is every side equally likely? If the dice are fair dice, then the probability of a particular side coming up is 1/7, whether it's the probability of a 1 or a 2 or a 3. For example, is P of 7, the probability of rolling 7, is that 1/7? I was curious. I have that pair of 7-sided dice. I rolled the pair 50 times a day for 200 days. That's 10,000 rolls of the pair of dice. It's like rolling one die 20,000 times. The result? 2,755 sevens out of 20,000 rolls. Now 2755 divided by 20,000 is 0.13775, whereas 1/7 is 0.142857. Is that far enough from 1/7 to conclude that the probability of 7 is not 1/7? Now, the null hypothesis, when you're testing a hypothesis, the null hypothesis is that there's no change, no difference. We usually represent that with an h sub 0. Sometimes you call it h naught. Okay, the alternative hypothesis is that there is a change. There is a difference. That's represented by h sub a. Some books use h sub 1. Okay, in this case, our null hypothesis, h sub 0, is that the probability of rolling a 7 is equal to 1/7. Again, that's because no change, no difference. Rolling a 7, same probability as rolling a 6 or a 5. Yeah, they're all the same. The alternative hypothesis is that there is a change. There is a difference. So in this case, that would be the probability of rolling a 7 is different from 1/7. Okay, so here's the way we'd represent that. There's no way we're going to keep writing out the probability of rolling a 7 is equal to 1/7. Holy cow. We would just write it this way. Let P equal P of 7, in other words, the probability of rolling 7. Our null hypothesis is that P equals 1/7, and our alternative hypothesis is that P does not equal 1/7. Okay, now the null hypothesis always has an equal sign. It looks like this, P equals. So it's of the form P equals P sub 0. For example, here, our null hypothesis is that P equals 1/7. The alternative hypothesis, H sub A, has a not equal sign, or a less than sign, or a greater than sign, so that it's of the form P does not equal P sub 0, like we have here. Ours is like that. P does not equal 1/7. Although it could be, under some circumstances, of the form P is greater than P sub 0, or P is less than P sub 0. We'll see examples of those later on. Okay, so P is probability of rolling 7. Null hypothesis, P equals 1/7. Alternative hypothesis is P does not equal 1/7. How do we determine which is true? We calculate the test statistic, and that's z equals P hat minus P sub 0 over the square root of P0, 1 minus P0 over n. Now here, P hat, again, that's the probability of successes, or really the proportion of successes in the trial. That's 2755 divided by 20,000. P sub 0 is the conjectured value of P in the null hypothesis, which we conjectured again was 1/7. Okay, so let's go ahead and plug those in. So P hat is 2755 over 20,000. P sub 0 we plug in as 1/7. N in this case is 20,000. Plug all of that in, calculate it, and we end up with z equals negative 2.0640. Well, what does that mean? Z equals negative 2.0640, or really z equals negative 2.064, is our z-score. Assuming the null hypothesis is true, this is what the distribution of z-scores would look like. We've seen this before. It's a normal distribution with mean 0 and standard deviation 1. Sometimes we call that the standard normal distribution. So we should get a z-score. 95% of the time, we should get a z-score between -2 and 2. Okay, although, as we've seen in class, it's really negative 1.96 and 1.96. So if we get a z-score that is not between negative 1.96 and 1.96, we conclude that the null hypothesis is false, because it's really unlikely that if the null hypothesis is true, that you're going to get a result in that range. Just not going to happen that often. In other words, if z is less than negative 1.96, or z is greater than 1.96, we conclude that the null hypothesis is false. Since our z-score is negative 2.064, and that's less than negative 1.96, we conclude that the null hypothesis is false. We reject the null hypothesis, h sub 0. Okay, now let's find the p-value. What is the p-value? This is short for the probability value. It's the probability that we would get a result this extreme, or even more extreme, if the null hypothesis were true. Okay, if the null hypothesis were true, the probability that we would get a z-score of negative 2.064 or even more extreme is, okay, we know how to do that. Okay, here's negative 2.064 roughly. We can calculate that on the TI. On the TI-83 under dister, NormalCDF, a comma b comma mu comma sigma, tells us the probability that a variable, which is normally distributed with mean mu and standard deviation sigma, will be between a and b. In other words, if x is normally distributed with mean mu and standard deviation sigma, this NormalCDF tells us the probability that x is between a and b. Now, if we don't enter mu and sigma, it's assumed that the mean is 0 and the standard deviation is 1. Again, that's what we call a standard normal distribution. So let's see what that would tell us here. Okay, so we want to enter NormalCDF. In this case, we want to enter NormalCDF negative 10, 2.064. And here's why. We want to know what's to the left of negative 2.064. Well, the left endpoint is really negative infinity, but there's no negative infinity button on your calculator. So it's good enough to enter something that's ridiculously small, like negative 10. I mean, that's way out here. So our left endpoint is negative 10. That's negative infinity for all practical purposes. And our right endpoint is negative 2.064. And we get 0.0195. So the probability that we get a result this extreme or even more extreme is 0.0195 plus 0.0195. That's 2 times 0.0195, or 0.0390. And here's why. You know, we could get a result this extreme by getting something that's to the left of negative 2.064. But in fairness, if we have gotten a result over here, well, that's equally extreme. For instance, if we had gotten 2.064, that's just as extreme as getting a result negative 2.064. That's just as extreme. And the probability that you get a result this extreme or even more extreme, well, this is 0.0195, and this by symmetry is also 0.0195. So that would be 0.0390. In general, when the alternative hypothesis is two-tailed, that is, when it's of the form p does not equal p sub 0, then the p-value is twice the area to the right of the absolute value of z. In this case, the area to the right of z in absolute value is the area to the right of negative 2.064. That's the area to the right of 2.064. And when you calculate that on the TI, you end up with 0.0195. And twice that is 0.0390. So your p-value, again, is going to be twice this area. Twice 0.0195, that's 0.0390. So our p-value is 0.0390. If the p-value is less than 0.05, we reject the null hypothesis, because there's less than a 5% chance we would obtain a result this extreme or even more extreme if the null hypothesis were true. As Mario Triola, a statistics textbook writer, says, if the p is low, the null must go. So because the p-value is less than 0.05, we reject the null hypothesis. Again, p, probability of rolling 7. There's a null hypothesis, alternative hypothesis. We reject the null hypothesis and conclude that the probability of rolling a 7 is not 1/7.